NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. Welcome to another episode of the High Impact Thesis podcast, and today we have our guest Aditi. Aditi, we're very happy to have you here at the High Impact Thesis podcast.
Thank you so much to both of you. Thanks for having me today.
All right, and today you're being hosted by myself, Christopher, and
Ahmed.
All right. So as usual, Aditi, we like to know you, the person, a little bit broadly about your research in the early part of a segment, and then we move on to very specifically what you do as a research on a day-to-day basis, and then we move on to more generally what is your research going to impact, what kind of impact will research have, broadly speaking, many years down the line, or broadly beyond Singapore and so on, and then we'll finally finish off with talking about what your interests are as a person. So that's the structure for our episode today. So tell us a little about yourself and generally what field you're in.
Okay. So I'm currently in my third year of PhD here, and I'm from India, born and brought up there. And currently I am working very, very broadly, if I may say so, on control of grid-connected photovoltaic power plants. To give you a little bit of background on photovoltaics and solar, so I think that in a quest of humankind to move towards a more sustainable and more environmental friendly future, we are moving more and more towards renewable energy sources such as solar and wind, and we want to reduce our dependence on fossil fuels and essentially any fuel that can be replenished. So
that cannot be replenished.
Yeah, that cannot be replenished. Yes.
All right.
So and solar, because it's very abundantly available. Yeah. It has been used quite a lot, and there has been significant advances in its infrastructure, not only on the hardware level but also on the control aspects of it. For example, in the last 1 decade, the electricity generation by solar has increased by more than 200%, which is a very big number. And this exponential increase is likely to follow in the future because first of all, the price of the solar panels has been steadily declining. Its production cost has been declining. There are more and more materials of solar panels coming up which are far more efficient than what we had to start with. And also these days, many countries have policies that are motivating and motivating people to take up more solar energy based systems. And one very big example is right in front of us. So there are these tensions between Russia and Ukraine these days, right? And part of the reason is that one country thinks that it has an upper hand over another country because of its abundance in fossil fuels and oil. So that is why now more than ever, we need to switch to renewable energy sources such as solar, not just because it's good for the environment and because of sustainable reasons, but also because of geopolitical correctness. Each country essentially wants to be self-sufficient with respect to fuels, with respect to energy, and they don't want to be dependent on others to not have this kind of situation that we are in today. Solar power plants can be of two types. They can be grid connected or they can be islanded. That is, it's a small solar power plant, and it's a kind of self-sufficient, providing energy to the households within its vicinity or to an industrial load. My work is on grid-connected photovoltaic power plants. So the energy produced or the electricity produced by the solar panels is injected or sent into the grid. And I feel like my work is more on the control aspect of the grid connected solar power plants. I'm working on a very tiny aspect of the control. I'm working on reserve power point tracking. But then again, I feel like this technology has the potential to increase penetration of solar power plants in the grid, and which can be something big in the future. So, yeah.
While we're still talking about the general solar energy industry that you're in, currently is the main hurdle of price out of the way completely? That because you mentioned there's politics and so on as well involved. Is the next big thing going to be about politics? In other words, from an engineering point of view, is it the best solution, or is it still debatable, I guess, in the industry as to whether it's a good replacement for fossil fuels? Because one thing that I guess outsiders don't, like I as an outsider, right? Like I mean, fossil fuels is like one of the strongest arguments. That fossil fuels are there day and night, right? So I'm not always thinking about two things like solar plus batteries. I'm just thinking of the fossil fuel. So from you as an engineer, generally speaking, is the next challenge just political will political? How do I phrase this question?
Geopolitical. Is that what you're trying to say?
So is solar the best from an engineering point of view? In what sense is it the best? In what sense is it better than fossil fuels? I think is what I'm trying to ask.
Okay, so fossil fuels, sooner or later, they are going to, the wells of fossil fuels, they are going to be finished, right? So I think
I don't know.
Until we are in the situation of urgency, until it is for certain that, because we keep hearing that 20 years or 50 years down the line, there will be no fossil fuels, and then we have to be completely dependent on renewable energy sources. I think that when that urgency nears to humankind, then they will be acting kind of more quickly to move to that next step. And in one way, that urgency is arriving in terms of each country trying to be self-sufficient in terms of energy for themselves. But at the same time, as an engineer, I would say that the technology is not quite there yet, that we can be completely dependent on solar or, as a matter of fact, any other renewables. One of the biggest reasons is that, and that is one of the actually main reasons that why until now it has not been adopted fully, and that is exactly what the researchers are working now today as well, is that there is intermittency associated with renewable energy sources, meaning that so we know that the sun's irradiance or the sun's intensity is not constant throughout the day, right? So the power that is generated at 12 noon will be much higher than the power that is generated at 5 p.m., right? But we as people, we cannot adjust our need for energy or power according to what is available or according to what is being generated by the solar. So this kind of intermittency puts the entire renewable energy fuels to question, and this is the solution. This is the problem that the researchers are trying to solve, be it in terms of control, be it in terms of materials, and be it in terms of optimizing with other energy systems, be it with batteries or supercapacitors, or in comprehension with other in fossil fuels, or many thermal power plants have a solar energy system as well. So in India, they have this thing that during peak loads, they use the solar energy generation, and for a constant load, they use the thermal power plants. So it's also about optimization, but I think it's like the solutions, I can say, on a very broad level are quite scattered right now. So I guess it's going to take some more time for everything to come together and make much more sense. And with that, factor of urgency when it arrives. I mean, things will have to come together at that point of time. There will be no other option, right?
Right. So. Okay. I want to ask a question about the solar cells themselves, but yeah, I'm not sure if it's within your, expertise.
No, I'm more on the control side of it,
Okay.
Not on the material science. No.
Actually, what I want to get to is that the problem you're working on, right, MPPT. Why does it exist?
Okay,
right?
yeah, sure, I can tell you that. Yeah.
Yeah. So just start from there, and then maybe later
sure.
we get into your.
So basically, I'm working on grid-connected photovoltaic power plants. As I already said, that the power generated at the solar panels will be transferred into the grid. Of course, there are many more levels of conversions and converters in between. But so the main thing about MPPT is that first of all, the efficiency of the solar panels is low. Even the best of the best panels today are like 25 to 30% efficiency, and that also I'm talking on the higher side. The commercialized solar panels have around 18, 19, 20% efficiency. As an example, the solar panels that I am working on in my lab have 17% efficiency, and it degrades with time. So,
do we know how is that calculated, the efficiency?
So
how do we know how much energy?
So efficiency is basically power out by power in, right? So the power in terms of or the energy in terms of solar, with respect to the power that is actually generated in terms of watts, we compare that. So that is how most of the energy we say that it's dissipated in terms of heat. So that's why the efficiency is low.
I can also just chip in there because on a square meter we know how much solar radiation comes, and so we know, for example,
so there's a specific spectrum that we calculate for, right? Or not the whole spectrum.
Mostly, I think it's visible light that you're concerned with, right?
Yeah.
So
I mean, whatever the solar panels can catch, right?
Can catch, right?
Yeah.
Okay.
Yeah. So, okay, that's maybe a topic for another time, but if someone wants to, let's say, emulate a small solar power system at their house, or for example, for me, I created one in my own lab. So if you have to choose lights to emulate the sun, you would choose the one that has the bandwidth or the spectrum that is closest to the sun.
Right.
Because that is what solar panels are designed for.
Yeah.
Which is like, I think, visible light. Plus,
I think it's
plus
light range.
plus minus.
Infrared, there's some UV as well.
There's
wears some glasses.
A little bit of each,
so,
on either side.
Okay, anyways, coming back to MPPT.
Right.
So, the efficiency is low. So now I can very briefly explain you how a power versus voltage curve of a solar panel looks like. It's almost like a bell curve. All right. So we know that on a bell curve there is a topmost point, right? So we call that as a maximum power point. Now, if we know that something has a very, very less efficiency, we'll definitely try to make it work as better as possible, or what I'm trying to say is to get that maximum degree of utilization, right? Mm-hmm. So we would want to extract that maximum power, right? Which on that bell curve is the topmost point, right? So tracking that maximum power point is known as maximum power point tracking. Mm-hmm. So I hope that's clear, right?
Right. So you have a curve, power versus voltage, right? So I'm assuming that you have to vary the voltage.
Mm-hmm. Yeah.
So what does that mean, varying the voltage? Because let's say you buy a cell, you buy an array of cells, and it says it has this much voltage, like 12 volts or 36 volts.
Right.
Then what does it mean, 36 or 12?
So whenever you see the data sheets of a solar panel or a solar array for that matter, there will be certain factors, certain parameters. So in terms of voltage, there could be open circuit voltage and there could be voltage at maximum point, right? So that we already know. We already have what is the curve as a user, we will know what is the curve of the solar panel at standard conditions, 25 degrees Celsius and 1000 solar irradiance. And we also have like different curves at different temperatures and irradiance, because the solar curve changes with differences in temperature and irradiance, right? So we know all these parameters. If I had a whiteboard and a marker here, I would have, I could have explained it to you. But yeah, we know these parameters, and we use essentially some sort of controllers to make the voltage operate at a certain point, so as to extract the maximum power possible that we can. And since I'm working at least in a grid connected system, we would convert this, because solar panels produce DC power. So we would convert it into AC and then inject into the grid.
So just to understand the way this works, you have solar panels, then you have cables that go, I guess, to a controller of sorts, and then from the controller you go to the grid for you. But for other people, like a household, for example, that might go to a battery to charge the battery.
Yes.
Right.
Yep.
So your work is primarily between the solar panels and the say charge controller, or is it part of the charge controller itself? Like, where does your code
charge controller basically comes into picture when you're charging batteries, because you don't want to overcharge them and stuff like that. So basically I'll tell you the whole system for me.
Yes.
So we have, let's say we take a very small system. We have a 50 watts solar panel, alright, which generates 50 watts of power. Then I will have a DC to DC converter, because I might have batteries in the system as well, and I might want to step up or step down the voltage. So I need a DC to DC converter. And then controlling the DC-DC side, because the input of the DC-DC is the PV voltage. Okay, so I will have the controller controlling this side, and then I have a DC link capacitor, and then finally I'm having a DC to AC converter. Inverter is there, and then finally through a AC link I am transferring the power into the grid. So this is the whole structure. So I basically work on the control of the DC to DC side and also the DC to AC side both.
Okay, so the way I see it is that you need a way to control the output voltage of the panel, right?
Voltage, power, yes.
I mean, to get to the maximum power, you need to change the voltage. So that seems to me the main function of the DC-DC converter.
Yeah, that's right. Yeah.
I mean, it's not the main, but it's one of the
functions. Yeah.
So you control the input side of the DC-DC converter to get the maximum power. And then you want to step it up or down. That depends on the application.
Yeah, exactly.
And then again, you convert it to AC.
And then just inject into the grid.
Right.
So this is what is maximum power point tracking. But obviously, MPPT is a very conventional control algorithm for photovoltaic power plants. It is still very, very widely used. However, it has many limitations. For example, I already told you that there is the issue of intermittency with solar systems, right?
Yes.
That means that the power keeps varying throughout the day. So that means if the solar intensity is varying throughout the day, the maximum power will also vary throughout the day, right? And so the solar irradiance is varying, the temperature is varying, and then we have our cloud cover. So if it's a country like Singapore, where the weather changes with the blink of an eye, so good luck with your system in that case.
Right.
Because if there is cloud cover, it is shading part of your solar array, your output will be decreased by a significant amount. Your the power and voltage curve will change. It might also have multiple peaks, so your control algorithm should be smart enough to detect the actual maximum and not the local maximum. So that's another thing. So essentially, in MPPT, if we are doing MPPT, the power keeps varying, right? That means we're injecting a varying power into the grid. which is not only detrimental for the grid but also highly undesirable by grid codes and standards. And by grid codes and standards, I mean the standards of countries like Australia, South Africa, Denmark, Germany. These countries have significantly good solar energy infrastructure, and so for them, the grid-connected photovoltaic power plants have to follow certain standards. So that is not allowed in these countries.
So when you say a controller, is it a digital controller? As in, how do you make the measurements and make the decisions? Is it the way it's physically connected, or is it like actual measurements? You have some code somewhere. What is this thing?
A combination of both. So,
Okay.
for example, in my system, I have very tiny two solar panels in my lab. I take measurements from there. I have my converters and everything. Hardware is there, and those measurements are sent to my controller. I use this Imperex boombox controller. I'm not sure if any of you have heard about it.
Well, it's an FPGA or like
Yeah,
what?
it's FPGA based.
Okay.
Yeah, exactly. So yeah, it's just a company who makes FPGA based controllers. So yeah, it goes to the FPGA controller, and then I have my code to change everything or whatever I want to.
Okay.
So that's how it works.
So when you send it to the grid, it's 224 countries. Like here, for example, what do you actually? What voltage is coming out? And what system?
Power.
What
You
comes
mean
in?
what power?
Oh, what power is what matters? Like, what do you give to the grid?
You mean to say, are you asking in terms of frequency? So from country to country, the frequency varies. For example, mostly in Asia, 50 hertz works. In US, it's 60 hertz, and so on.
So I think he's talking about like the power range that you need to like.
I
see to
mean,
the
it
grid.
depends on the size of the solar power plant, right? So it could be, I mean, ideally for a big solar power plant, because mostly big solar power plants are connected to the grid, which have the capacity in megawatts at least.
Say that again.
Megawatts, which is
No,
like
no, I mean,
comparable
you mean-
to thermal power plants or something.
Oh, actually, I'm wondering whether your system is for big guys or like homes.
No, mine.
Like
So
if-
mine is grid connected, right? So mostly grid connected systems, grid connected photovoltaic power plants.
But yeah, sorry. So grid connected for you means people producing megawatt level, not like because there's grid connected in the sense of people can put electricity back on the grid and earn some money, right?
I mean,
different from what you're doing.
essentially the control structure that I'm working on is applicable for any level.
Okay.
So it can be applicable for both. But if we talk in commercial aspects, it has to be big if you're sending it to the grid. The one that you're talking about is when people have rooftop solar panel systems, and they use up they're able to use up all the energy. If not, they send it back to the grid, and they actually sell it to the grid as well.
So your MPPT would work in that case as well.
Yeah, both cases.
Okay.
So before we get into what you actually do and how you're tackling this, just a little bit more background. So this problem is associated with solar cells and wind turbines. Is that it? Or are there any other technologies that this problem appears in? The tracking of the maximum power point?
I'm aware of only these two. I'm not sure if there are other renewable energy sources which have the same issue. But yeah, for sure, the pattern of the uncertainty is always associated with any kind of renewable energy source. So, I mean, intermittency is always an issue with solar. So that's why most of the photovoltaic power plants, they'll always have some sort of energy storage system or backup or something like that.
Yeah, I assume tidal energy. I'm not sure how implemented.
Yeah, there is.
But I assume there is definitely some uncertainties.
Right.
Yeah.
Yeah, so the algorithms, the techniques you're developing, like you're developing it for prototypes, I assume.
Yeah.
So then,
Lab prototypes. Yeah.
is it easily transferable to large scale projects and systems?
Yeah.
or do you have to do some extra modification?
No, I don't think so. There will be any extra modifications. The good thing about my control algorithm is that it does not require any extra hardware, additional hardware measurements or any other devices. It can be implemented in existing solar systems. So that's the good thing about my RPPT algorithm that I am working on.
Oh, okay. So
So-
we'll get to what RPPT is. But
Yeah, sure.
so you're saying, I assume that you're saying like you don't need to get into the individual arrays. You just care about the total, like the whole.
Yeah, the whole array or the solar, just
I
the
see.
solar side of the solar power plant as a whole.
So if I have 5 million panels, they all go through your system, or each panel has its own of your system?
No, it's all together. Because the control
Oh.
for them is also all together. Because we don't take a solar panel as an individual entity. We take a solar array as an entity to be controlled. A solar array could be solar panels in series, solar panels in parallel, and also combination of the two. So that's what we mean by solar array, and that's what we try to control.
Okay.
All right. So let's get to the problem.
Yeah.
I mean, I'm also in power electronics, so I have a little bit of background in that. So basically, you have a curve, and this curve is changing with time,
Yeah.
and you're
Changing with irradiance and temperature and
Right.
which factors also change with time. So indirectly, yes.
right, like it changes with many variables,
Yes, yeah.
and your goal is always to find the maximum
In
point.
MPPT, yes, yeah.
on that curve.
Yeah.
So yeah, maybe tell us about how people before you have approached this, and then what are you doing that is
Okay.
yeah improving.
So there are multiple approaches available to track that one point. There are approaches based on perturb and observe. That means you start on a particular voltage and then you measure the power at that point. And if the power is not desirable or it's not the maximum, you go a voltage step further and then check. But this can obviously take time. It's not very fast. Then there is, there are different types of controllers. For example, there will be perturb and observe is voltage based. Obviously, there will be. Then there is incremental conductance. There could be current based or power based. So there are many of these controls available. The most optimum one, I would say, in MPPT is the perturb and observe one, and then there is another perturb and observe algorithm in which the voltage step size is adaptive. It's adaptive based on how much is the difference between the desired power and what is the actual power right now. So the voltage step could be increased or decreased using that, and that's a fairly fast technique. I would say it's one
But
of the best among
we
the
don't
existing.
always know what's the maximum power available, do we?
No.
That's another problem,
That's
right?
the thing. Yeah, that's the thing I address in my work. So
Okay, that's interesting.
yeah. So this is MPPT. Personally, I find this part the most interesting because now we know what are the limitations of MPPT. Now I'm going to tell you what is FPPT, that is flexible power point tracking. It's like one step ahead of MPPT. So we know that we cannot inject variable power into the grid because of all these limitations, right? So what do we do now? Because we have to use the solar, right? So what researchers came up with is FPPT or flexible power point tracking. So basically, they pick a reference power, right? So if it's a 50 watt system, let's say, they pick a 40 watt or 35 watt power reference and they will operate at that. So now they have a power reference to operate at, and instead of tracking the maximum power or what it is, they will always no matter what the solar irradiance is, they will always track 35 watts only and they will inject that into the grid. So it is constant. So there is no issue of intermittency, right? So that is FPPT. But at the same time, now we don't know what is the maximum power available, because we know what is what we are injecting. We change the voltage operating point according to that, but we don't know what is the maximum power available. For example, there could be a disturbance in the grid. There is a transient or a contingency, or if it's a grid connected system, one of the other power plants attached to the grid has failed. So now the solar power plant, on which I have my control on, needs to supply extra power. But my solar power plant does not know what is the maximum it can supply in terms of FPPT. So that's one disadvantage. It cannot have any, it cannot provide any power reserve, essentially. So power reserve can be defined as the difference between the maximum power and the operating power. All right. So it does not know what is the maximum, so it does not know what is the maximum, what is the power reserve available. So that's one drawback. But nevertheless, at least it fulfills the limitation of MPPT of injecting a variable power into the grid. So that's there.
Wait, so just to backtrack a bit. So you're saying MPPT, when it's implemented, the power output varies?
Yeah.
And people are trying to resolve that particular thing. So the tracking is okay.
But the
Why do people
injection
invent-
is not okay.
So the MPPT, the goal was just to track the maximum, to get the
Yeah.
maximum out of
Yeah.
the solar panels. You didn't care about consistency on the output side.
Yeah.
All right.
So
now you care
there
about-
can be, in order to have consistency, if someone has the money, they can implement, or they can add some energy storage systems. But the cost of the whole system will sharply rise with energy storage. You can have consistency with that, and same for the FPPT systems. You can always have a certain amount of power reserve available in terms of physical battery. We don't know what is the maximum, but we know that, okay, in terms of contingency, if some other power plant fails that is connected with the grid, my solar power plant has this many watts of power that it can supply in that case. But yeah, it's very, very expensive adding an energy storage system into the solar power plant. So this means that we need essentially a control algorithm that not only injects a constant power into the system, but is also able to identify what is the maximum power available, right? So that's basically the need of the hour, and that is what I call as reserve power point tracking, or RPPT. This is again like a successor to the existing MPPT and FPPT algorithms. So it works such that it is not only injecting the constant power into the grid, but it is kind of scanning the power voltage curve of the solar array, such that it knows exactly where the maximum power point exists. So it knows what is the power reserve available. So in terms of an issue, it can always go back to the operating point at the maximum, and then inject that into the grid. So this power reserve can be treated as a virtual battery, actually. And for large scale photovoltaic system, it can replace part of the physical battery, which will save like 20 to 25% of the cost of the batteries. So that is what my work is about.
So currently the reserve, if you have this system that injects just a portion, you don't know the reserve, then the reserve is just discarded, or
it's essentially you mean in RPPT or FPPT?
No, in the early
in FPPT, you don't know what is the reserve, so it is not being used. So I said normally, in case of FPPT, the systems are a little, over design. No, that's not the term. They are designed for higher the rating than they're required to have.
Okay.
So that it can always work on FPPT because you never know what is the maximum power point. So essentially, for like a 250 watt system, you will need to design your solar panels to be like 300 or 350 watts and then operate at 250 reference and inject that into the grid. So in case of RPPT, you don't have to do that as well because you know at all times what is your maximum power available.
Okay.
Yeah.
So what happens now? Like after now you have you added this part where it scans the whole curve and you have the maximum.
So in my system, in RPPT, it scans in such a way that it first of all it scans at a very very high frequency, and it happens in such a way that you know what is the maximum power point at all times, and this the scanning is happening such that the average power in a particular time duration will be equal to the reference power, and that is the power that is to be injected into the grid. And now this scanning frequency is much higher than the actual grid frequency. So for the grid, it is essentially constant power, because if the grid is, let's say, at 50 hertz, the scanning is happening at a much higher frequency. So for the grid, it is a constant power injection. It's not actually varying like this on the curve. And the speed of tracking or scanning is so fast that even the temperature and irradiance won't change very quickly. At least within one cycle, it will not change. And I have a mechanism in which whenever for a certain amount of voltage, whenever it changes, my data gets stored in a matrix, and then I know exactly what is the shape of the PV curve based on the data I have stored. And so hence I know what is the maximum out of them all, what is the maximum power, what is the corresponding voltage, and that's my MPP.
So the scanning is happening constantly,
yeah, because over a time period of scanning, it is done in such a way like it has certain points where it stays, certain reference points on the PV curve. So on an average, in one particular time duration, it's equal to the reference power that is required to be injected into the grid.
And once you've designed the system, does the reference, so the reference, is it pre-programmed, or is it something that an operator of the system can program?
No, so the reference, I have a shape of the reference voltage programmed, but then the shape and the duration is same, but then in the shape itself, there are 3 points at which the voltage is supposed to stay, and for the time for which the voltage stays at those 3 points, the reference voltage, those vary according to what is my reference power. So if my reference power varies, those small time durations within the shape also vary. I really wish I had a board right now to explain it to you that way.
Okay, so to summarize, the reserve power point tracking, you're able to do what MPPT does to track the maximum power, and also be able to send the
constant.
So you're not discarding anything. I guess like the reserve PPT.
Yeah, we know what is the reserve. Yeah.
So wait, you know what is the reserve, but what do you do with it? Or what?
Okay, for example, you might know this because you have power electronics background, or it's more related to power systems, I would say. So in a grid, there are some transients, they are bound to happen, right? So a very common one is frequency deviation. So frequency has a certain range. Let's say if it's 50 hertz in Singapore or mostly Asian countries, it has a certain range within which it should lie. It should not vary too much. And many a times it tends to drop. If let's say it drops below 47.5 or 48.5, these numbers vary from country to country. So the system is basically having a contingency, and if there was a thermal power plant, because of the generator inertia of the thermal power plant, the power would start increasing, that is being injected into the grid to make up for that frequency drop. All right. So that would imply within few seconds the frequency would go back to its nominal range. All right. So now, if I have, instead of a thermal power plant, if I have a solar power plant, I need to have the same inertia, but there is no generator. So here we have extra power reserve. So that power reserve can actually be treated as having a virtual inertia. So the power injected into the grid based on the frequency can be increased now, and now the solar power plant is actually providing a grid frequency support. So that's the one of the applications, you can say, of having this power reserve.
I'm not in electrical engineering, so it's passing over my head a bit, because I'm wondering, how do you store this thing, the reserve that you want to deploy when there is a frequency drop?
It's there already.
Yeah, it exists. We know it's there, but we are not using it.
Okay,
But
now,
we can use it when we need to. That's the
So
thing.
the question was, how much is there?
Uh,
And that's what she's solving.
okay.
Because before, there was no way.
Yeah.
So now we know that it's there.
Yeah.
So then people can be at peace knowing that there's that much reserve.
Yeah.
But-
And if needed, we can use it.
So what happens when we're not needing it?
You can always use it to charge the batteries
Oh, okay.
or some other purpose or any other external loads
Okay.
which are inside the solar power plant maybe.
So you mentioned the FPGA controller that you're using. What other tools do you use in the lab in your PhD?
Tools, well, I have solar panels.
Uh-huh.
Then I have the DC to DC boost converter I'm using.
Right.
So I'm using again IGBT based switches.
What is IGBT?
It's kind of a switch.
Okay. So this stands between the DC converter and...
It's part of the DC to DC
Alright,
converter. So yeah.
And what language you use to program?
So the good thing about this FPGA controller, so my controller is basically Imperix boombox controller. It has various versions. Mine is I think 3.0. It is an FPGA based controller, and the good thing about this Imperix controller is that you can use your MATLAB codes. So
Okay.
I'm using MATLAB. So very little modification is required from your simulation to actual hardware controller codes.
Nice.
So yeah,
That's
that's the good thing about using Imperix.
So one
and
issue,
it's a
yeah.
very powerful system. It can go up to switching frequencies of 70 kilohertz.
Yeah, FPGAs are
That's very
super
powerful,
fast. Yeah.
Wait, 70 kilohertz is fast?
For switching, yes.
Yeah.
Okay.
I mean, it
Okay.
depends on the application, right? I mean, some power applications require megahertz switching. Some of them require
Yeah.
few kilohertz.
Okay.
For example, I don't go beyond 15
15 hertz?
Kilohertz.
Okay.
So one issue I have with FPGAs is that, at least the one I'm using, which is the one embedded with the DSpace controller,
Okay.
it takes a lot of time to upload your code. How do you... I don't know if that's inherent to FPGAs or just the DSpace one.
I haven't actually never worked on DSpace. But in case of Imperix, it doesn't take a long. It would take like maybe 2 minutes for the code to load in the
Right.
controller
Oh, sorry.
software.
I'm mistaken. I don't mean actually uploading your code, but just
Running it?
translating it from like the MATLAB environment.
No, but that's the good thing, right? I'm using MATLAB only. And then there
Okay.
is another integrated software of Imperix in which you can see all the live values of your sensors. Basically, you can connect your sensor wires to the boombox controller,
Right.
and then in the boombox Imperix software, you can see all the live values over there. So
Oh, that's
and
good.
it's like integrated with MATLAB itself, so it's a good system, yeah.
Right.
It's an interesting name, though, Boombox. So
It's
this...
it's from the company name is Imperix. It's a Switzerland-based power electronics company.
Okay. So this
Yeah.
boombox, physical connecting it to you is just USB?
Yeah, USB and to my PC and Ethernet cable. Either or, either of the
Okay.
things. Yeah.
Okay, cool. So because we do want people who are listening to know what's what are the tools. So maybe they want to join you in your lab sometime. They should know what to
Sure.
learn. Okay, so what are the discoveries? Or what are some things you have? What can we say? Things you've achieved in this RPPT.
Well, experimentally, I was able to prove that this algorithm is indeed very efficient, and I was able to test in changing irradiance conditions. So I actually have LEDs in my lab with solar panels, and those LEDs have a separate dimming circuit. So I can control the dimness of the LEDs to emulate the changing irradiance of the sun. So I have tested under those conditions, and I have tested under partial shading conditions. That means whenever there is a cloud cover on one of your solar or any part of a solar array, how will the system react? Because it tends to create multiple peaks, and then your algorithm should be smart enough to track the correct one and not the local maximas in that case. So I have tested in that case also, and some these things. Yeah.
Okay.
So
That's
in
what
your
I-
algorithm, are you scanning the whole curve, the whole voltage
No.
range?
So that's obviously limited by the DC-DC converter voltage limits. But most of the range of the PV curve, yes. At least it definitely includes the portion in which the maximum power point exists. So there's a range in which the MPP exists. There was a study. There's actually quite a bit research on this topic, that there is a certain range in which the MPPT all exists, even when these parameters of irradiance and temperature are changing, that MPP will always lie within that range.
Oh,
So I make that sure that whenever I'm scanning, that range is always included.
Yeah, I mean, also just intuitively, you think of the curve. At the beginning, you have very low voltage, so you don't expect high power there. At the end, you have very low current, so
Yeah,
you also don't
exactly.
expect high power.
Yeah.
But it's not in the middle, of course. So it
Not
varies.
exactly.
Yeah,
No.
yeah.
It's a slightly tilted bell curve.
Yes,
I would say.
yes.
One side the slope is quite linear, the other side it's quite steep.
It because of
It's
the
like
current
this, yeah.
curve. Yeah, because yeah. So the way I understand your algorithm works is that you're doing extra or additional steps on top of the FPPT. Is this correct? So does it make it less efficient?
No. I wouldn't say that there are extra steps. I would say that the way in which I'm performing my operation, it covers FPPT.
Okay.
So
Okay, so same amount of effort or similar.
if you're talking about in terms of complexity, no. The RPPT is definitely more complex as an control algorithm.
So are
But
you paying for the
otherwise-
extra? So I mean, you're getting additional information about the curve. So are you paying for this in complexity and computational effort? Is this a trade-off or?
Not. It is a little bit of trade-off, but not something very big that someone needs to really take into account while designing the system. I mean, it's not big enough to affect RPPT operation. No. I agree that there is definitely a large amount of data storage space required, and if it's a big power plant, then definitely a lot more. But at the same time, there is an upside to this data. Since you have all of this data, I mean, this is one direction that I could go in the future go in. since you have a large amount of data, you can always use this data to kind of monitor the health of the solar panels. So that's one direction one could go
Right.
in to use this data. So
You can also, I'm not sure, but could you like predict like weather
Maintenance.
conditions,
Yeah.
for example? Or
I am not.
I don't know
sure
about the
that.
maintenance thing, but like I would imagine because you already know the maximum power available, and like you can see it, for example, going down with time, and then you can predict.
I mean,
Is it-
definitely, there would be some sort of a lot of analysis required for that. First of all, also taking into account that whenever you stored that data, what were the temperature and irradiance conditions at that time. So, I mean, if you know the temperature and irradiance, you can, with the shape of the curve, you can probably predict what kind of shading pattern was there. Cloud cover pattern basically, and it can be translated into shading pattern on the patterns on the solar panels. You can maybe do that. That is also a possibility, but definitely I think it would require a lot of analysis.
So how would the maintenance thing work?
That's again a potential area for work. But then again, you have lots and lots of data of the solar panels. Based on the data, maybe you can predict, like you know under what temperature and irradiance conditions what was the curve. So, and you also have the reference data sheets of the solar array or the solar panel, so you can compare and see what is the health, and depending on the deterioration rate of that kind of solar panel, you can somehow make a relation with the maintenance, like when should be a maintenance for a particular solar panel.
So are we talking about also using machine learning here? Machine learning
Maybe.
and neural networks?
Maybe. It's possible, yeah. Yeah, I mean, if you have such large amount of data, it only makes sense to use some machine learning models, right?
So are we there, like, in terms of solving this problem? Like, is this all that we can do? Or are there still gaps?
I mean, this much is done from my side so far, but there are definitely other things that I'm working on, which can be taken as maybe future work. So, with respect to the scanning frequency and the shape of the reference voltage that I'm using, I can somehow...
What's that? What's the shape?
The shape of the reference voltage. So I have a scanning frequency, right? And then there is a shape of the reference voltage, because there are certain points at which my voltage will, at which my operation point will stay at certain voltages. So it's in terms of a shape. They are not
fixed intervals.
No, because my power reference keeps changing, right? So, and in order to get that much power reference as an average of my scanning power, I need to change something, right? So those small time durations are my parameters for the that are related with the power reference. So that shape can be somehow used. It can be reshaped, or it can be used to potentially shape the DC link voltage, so that you know what is the amount of you can control the amount of current, and then you can because capacitors are always oversized, right? So maybe you can slightly reduce the size of the capacitor with that. So that's one area. Okay, speaking of size, you are switching at relatively high switching frequency. I mean, it's not the highest, but it's still high compared to other power electronics applications. And I would imagine this would generate more heat. There are switching losses. Yes. Yeah. That's something I could actually work on. In my current system, there are a lot of switching losses. Yeah,
Right.
I can optimize the system to where I don't have to go so fast. I can definitely do an analysis with respect to the switching losses and the size of the system and efficiency of the panels with respect to how much switching I should be working on.
But I mean, on the other side, you also have the new materials, the wide bandgap transistors.
Yeah, but I mean, I have to work with what I have in the lab right now.
Right,
I'm not going to work
But yeah,
on
I mean, in
those
terms of
high-tech materials.
future, right? Like,
Yeah, definitely.
it might not be that big of a deal.
Yeah, and also right now the lab prototype is a very small system.
50 watts, is it?
Yeah, it's very small.
Yeah.
So
But if I want to get it for 500 megawatts, there's not a lot of extra work that needs to get done, right? So like one
Yeah.
week you tweak your code and then we deploy
and
it.
that's
But
what
then-
I was coming to, that in such a big system, the switching losses might be kind of negligible.
Okay, so it gets better.
For a 50 or 100 watt system, maybe like 5 or 10 watts is still significant, but for a 500 watt system, it's nothing, right?
Okay, I see.
So it also depends on the scale.
Have you thought of patenting your work or parts of your work?
It is patented.
Oh, you did. So you already did.
Yeah,
So
it
how was
is.
that? How was that like going through that process?
It was an interesting process because it's different from how you write papers. It's very different on how you write a patent application. Of course, I had help from my team and everything, but I would also say it's kind of less grueling than the paper process.
Okay.
Because in papers, you kind of get, need to work constantly to make it a really nice version of a publishable document. But a patent has to be very crisp of what is the technology about, and you need to give the proof, and that's it. You don't need like a lot of
Discussion.
and it's very crisp. It's very to the point.
Okay, that's nice. Congratulations. Yeah.
Congratulations.
I was thinking about it. Yeah.
So this patent, it means if I want to use this technology, I have to pay you quite a bit.
Not me. The license was transferred to NTO.
Your name is still on the patent, though.
Yeah,
Yeah.
It's an IP. It's very confusing actually, the terminology. It's after getting registered, it's called IP, intellectual property. So
All right, so you get paid, but in a roundabout way. Okay, so the state of the industry now is that they use MPPTs, I suppose. In the future,
FPPTs, yeah.
MPPTs and FPPTs.
Yeah.
And the future you dream of is one where
Yeah.
RPPT
Yeah, definitely.
is deployed.
Definitely, because this technology really does have the potential to increase solar energy penetration.
Okay.
So, yeah, maybe you never know someday.
Okay. I think we can end with more. I mean, my last question on this, on the solar aspect of it. So, this is a general question, right? You're in the solar industry, and as an engineer in the solar industry, you understand the hurdles, I guess, right? So this is just generally, what are some other things as someone who is in the solar industry now, it's a hot industry, right?
Yeah.
And I'm just wondering, you as an engineer, what are some other challenges you see? So these might not be the ones that you're solving, but just generally, do you see other things that are roadblocks that people listening might also consider working on to complement your efforts in moving the world toward more reliant on renewable energy?
I think whenever you talk about solar, there is definitely a question about integrating the energy storage systems. So that's I mean, they essentially go hand in hand, solar and energy storage systems. So many people are in my field are also working on integration of energy storage systems and supercapacitors along with the solar, and how to optimize the entire system. So yeah, that's one field that people can be interested in, and
Optimizing the whole system.
yeah, optimizing. Then there are like battery management systems, on which I think a significant amount of work has been done already. But yeah, I mean, there are a lot of new concepts these days, like supercapacitors and second life batteries, which are very interesting to me. I don't know a lot about these things, but I would definitely want to learn more, and there's definitely a lot of potential there to work on. Yeah.
Cool. So great work, and it's very good and relevant work in today's world. And so we hope that listeners, if you're interested in her research specifically or research in renewable energy, you've learned something exciting. And now we'll move on to you as a person.
Okay,
Um,
sure.
Yeah. So towards the end of the episode, we'd like to take a sneak peek into your life,
Right.
outside of the lab. What are your interests? What do you do, for
Okay.
hobbies and all that?
Sure. So I'm a very organized person, and why I say this is because I like categories and I like dividing stuff. So my hobbies and my interests also I have categorized into two types. So my activities and my hobbies are either based on improving my physical health or my mental health. So in terms of physical health, I try to do any activity that I enjoy, because I cannot do a workout that I'm not enjoying. And it's
I
also
agree with you.
hard to stay consistent with a workout that you do not enjoy. So I thoroughly enjoy yoga. I do it 3 times a week. And
nice.
I like dancing, I like Zumba. Then I love taking long walks and hikes because I really like to be in the nature. I think there's a certain calmness when you just take long walks in the nature.
Right.
And sometimes I would listen to a podcast while walking.
like the high impact thesis podcast, right?
Yeah, sure. No, I will definitely.
Okay.
So,
Okay.
Yeah,
Thank you very much.
and on the mental health aspect, I mean, podcast is also included in mental health aspects. I actually enjoy cooking a lot. I think it's very recreational, and it somehow falls under both categories, because it's recreational for me. And at the same time, because I want to be better physically, I would try to make yummy recipes in the healthiest way possible. So that's one thing. Besides that, I enjoy sketching portraits and also clicking portraits. But unfortunately, I do not get as much time as I would like to spend on photography. But yeah, this is something I like to do, and that's pretty much it.
All right. That's pretty interesting.
Yeah.
But you're also part of the student
Oh yeah.
activities, student
Yeah.
clubs here,
Yeah.
right?
Besides these, I am active in the Triple Graduate Students Club and some other activities in NTU. So that has been a good nurturing place as well, to get to know more people within your own school, working on different topics. It has not been the most exciting place because of the pandemic, because of all the restrictions of meeting and everything, but still I think we did what we could. And it's been good experience in Triple GSC so far.
Great.
Yeah.
All right.
Thank you.
So as our guest, we're going to give you some chocolate.
Okay.
Are you gonna eat the chocolate since you lead a healthy life or not?
I like dark chocolate.
Okay.
So I'm gonna take the dark one.
Okay. All right.
All of them.
Aditi, thank you so much for coming to the High Impact Thesis podcast. You have talked to us about supplying consistent power to the grid, right?
Yeah.
So you're in this solar industry that is booming. So very exciting work, and congratulations on your patent. It's very good to hear this. And so until next time, this is Christopher and
And Ahmad.
All right.
All right. Thank you, guys.